Okay, so let's talk a little bit more with horizontal asymptotes and how to deal with when we're finding as x is approaching infinity. So if we were looking here at the limit as of 1 over x as x approaches infinity, if I put infinity in, this is basically saying, and again, infinity is not an actual number, so it's kind of hard to conceptualize, but if you think about it, we're taking 1 and we're dividing it by a ginormous number. Like 1 divided by 100 million. It's going to get, as we're getting closer and closer to infinity, so as that number like 100 million, 200 million, this value is going to start approaching 0. Because again, it's how many times can this value go into 1? 0 times. Okay, same thing here. Even with the negative infinity, as we take 1 and we divide it by a ginormous negative number, so a really small number, I guess, if you think about it that way. But if we take it and we divide it by negative infinity, that's also going to be 0. And the same thing's here. This would be 3 divided by infinity to the 4th power. So 3 divided by a big, huge number is going to give you 0. So the limit as we're approaching these infinite numbers, as we have this variable underneath, is always going to give us 0, and that's what gives us this next formula. So this theorem, if n is a positive integer and k is a real number, then the limit as x approaches infinity of k over x to the n is 0, and the limit as x equals negative infinity of k over x to the n is also 0. So k is just a number, so it can be something like 3, so 3 over x to the 4th. So we can use this to help us when we're evaluating gross limits like this, because again, right now, if I substituted in infinity, I'm going to be in that indeterminate form. So we talked in the last section about indeterminate form of 0 over 0. Then we talked about vertical asymptotes in this section where we have an indeterminate form where you have a non-zero number divided by 0. Now we're going to talk about a different indeterminate form, and that's the form of infinity over infinity. So if I substituted infinity in for x in the numerator and denominator, I'm going to have a huge number in the top and a huge number in the bottom. It's going to be infinity divided by infinity. And that doesn't equal 1, which I know a lot of us have been taught, like x divided by x is 1. But again, infinity is not a specific number, so we can't use all those properties. So what we're going to do is we're going to, kind of how we did that math magic before in previous sections to get it so our function was in a way that we actually could evaluate it, we're going to do the same thing here. So the trick when you are working with these types of functions is to, I always tell students, the math magic that works the best in these is if you go through and you multiply both the numerator and the denominator, because again, we have to do the same to keep it balanced, by 1 over whatever the highest degree term is. So this is x squared, so it's going to be 1 over x squared. Same thing down here, again, to keep this equation balanced, whatever I do to the top, I have to do the bottom. So again, for both of these, the largest power any of these x's took on was squared, so I'm going to multiply everything by 1 over x squared, which is the same thing as dividing by x squared. So when I do that, watch what happens. So when I distribute this to here, I'm going to get 3x squared over x squared, which is 3. You know what? I'm just going to show this. No, you guys can see it. And then here I'm going to get minus x over x squared, which reduces to 1 over x, minus 2 over x squared. And then that's all over, when I distribute this down here, 5x squared over x squared is 5. 4x divided by x squared is 4 over x. And 1 times 1 over x squared is just 1 over x squared. So now what I've done is I've gotten it into a form, one of these forms, which is great. So I can actually go through, I can use limit laws now, along with this new theorem, to evaluate this. So I can move that limit all the way through to each piece of 2 over x squared, all over the limit as x approaches infinity of 5, plus the limit as x approaches infinity of 4 over x, plus the limit as x approaches infinity of 1 over x squared. So now I can totally evaluate this. So this is the limit of a constant. That limit as x approaches infinity of 3. So we learn with limit laws, that's just 3. And now we can use this positive integer, this formula or new theorem that we just learned. So 1 over x, that matches with having a number over x to a positive power. So that's going to be 1 divided by 0, which again is 0. Over here, same thing. I've got my k value is 2. And then I've got over x squared, so I'm going to use that property, and that's going to go to 0. So that's going to be 5. This goes to 0, and this goes to 0. So now I'm able to actually evaluate that limit and say it's 3/5. Let's do some more. So evaluate the limit as t approaches negative infinity of t squared plus 2 over t cubed plus t squared minus 1, and state the corresponding horizontal asymptote if applicable. Okay, so again right now, if I substituted in negative infinity for t, I'm going to end up getting a huge number on top and a huge number on bottom. So this isn't going to work. I'm going to be in that indeterminate form. Okay, so again, what we're going to do is figure out which one of these terms has the highest exponent. So looking here, we can see that highest exponent is 3. So I am going to multiply the top and bottom by 1 over t cubed, which is the same thing as basically dividing each term by t cubed. All right, so when I do that, I get the limit as t approaches negative infinity of t squared divided by t cubed is 1 over t. 2 times 1 over t cubed is 1 over 2 over t cubed. T cubed times 1 over t cubed is 1. T squared times 1 over t cubed is 1 over t. And then I get minus 1 over t cubed. So now again, I'm in that form from before where when I evaluate each of these pieces, the limit as t approaches negative infinity of 1 over t is going to go to 0. The limit as t approaches negative infinity of 2 over t cubed is going to go to 0. And then I'm left with 1 plus 0 minus 0 in the denominator. So I am left with 0 divided by 1. So that's going to give me just 0. So this means we're going to have a horizontal asymptote at y equals 0.